Right, so what we're going to do today is we're going to go over the practical, just briefly from last week, and then we're going to go over some more aspects of how stable isotopes are used in this case, mostly paleoceanography. Okay. So this was the first part of the practical where we had to do some kind of rearranging of these equations. So the question up here is asking you how you get from the composition of two phases, okay, to the fractionation factor. Okay, so the kind of equations that you kind of need to pointer options. You need to know that the fractionation factor alpha is just the absolute isotope ratio between two phases. Okay, and then there's this term that we use to describe isotope ratios, because it's very hard for us to measure the absolute isotope ratio of anything. So we use this term delta notation, which is the ratio in the sample, divided by some arbitrary standard. Okay, and for water isotopes, for oxygen isotopes, we actually have two standards, and that comes into the practical later on. So how to rearrange those is here. Most of you guys went through that in the actual practical. I'll post this PowerPoint on the Learn site, so you can, if you're unsure about it. And then the next section was basically asking you to write what are the assumptions made. Now I put this in the practical because this is the kind of add-on to some question in an exam. So you might usually have some kind of thing where you get an equation, some numbers, you plug them in, chugs out an answer. But what quite a lot of people fail to get marks on is the understanding what's really going on with that equation. What are the assumptions that are going into something? So in this case, we need to think about what are the assumptions when we're measuring paleo temperatures. So we're looking for things like, are the two phases in isotopic equilibrium? In the case of oxygen isotopes in carbonates, we might be looking at what do we know the isotopic composition of both of the phases? Okay, so in oxygen isotopes, that's quite often not the case. Okay, and then additionally, we'll see today there are some other issues about whether the oxygen isotopes actually obey the perfect thermodynamic relationship anyway. So hopefully you'll learn a little bit more about this question today. So the other part is describing why we get the temperature relationship. So in the terms of the top one, why would the magnesium-calcium ratio of carbonate change with temperature? Okay, so you're basically looking at element partitioning here. So the mineral is calcium carbonate. Why would magnesium fit into that structure? And why would the amount or the partitioning coefficient of that be temperature dependent? Okay, so in that case you're thinking about, well, higher temperatures, you're looking at more disorder, more mixing. Lower temperatures, your thermodynamics is dominated by the lattice strain of fitting an ion or an atom that's the wrong shape into the calcium carbonate crystal lattice. So you're really coming back to that delta G equals delta H minus T delta S. That's one of the basically the critical things for describing why you have these temperature dependent relationships for element partitioning and for the isotopes. So again, there's going to be in answering this question, if this was in an exam, you'd be looking at explaining that there's a temperature dependence on the disorder term in the mixing of isotopes between all the phases, but then there's some kind of term that dominates at lower temperatures. Okay, the enthalpy, of basically unmixing of the isotopes. Favourably, we want to be in one phase rather than the others because of the bond strength. So this is the kind of the plug and chug part of the practical, where you're basically asked to choose some values for the element ratio and the isotopic compositions based on these graphs. So for the Holocene, I've shaded in kind of yellow, and the LGM I've shaded in green in here. So you've got to pick a value of the magnesium-calcium ratio and the oxygen isotopes here. And you can see I've just started to fill in this table here. The next step is to do this conversion, because oxygen isotopes have two standards. Okay, so if you're comparing delta values between two different phases, you do need to make sure that they are you are comparing kind of apples with apples and not apples with rambutans or other exotic fruit. So again, that's just plug and chug. You put the numbers in the equation, you get so in this case, where paleo temperature can be calculated from magnesium-calcium ratio, using this equation up here, very simply rearrange that, kind of divide by 0.52, take the natural log of both sides, divide by 0.1 to give you the temperature in Kelvin. You can then convert that into Celsius. And then the next part is looking for what, if we know the temperature and we know the oxygen isotope composition of the carbonate, what's the oxygen isotope composition of the water? Okay, so we can do that by simply rearranging this equation up here. So that gives us the oxygen isotope composition of the water. And then another kind of describey bit of the practical. So this is, again, where kind of more marks kind of get picked up in kind of an exam situation, where rather than just plugging in, getting the right answer, I should also explain that once you get to the final answer stage, you should always be thinking about what's an appropriate number of significant figures. So, for instance, my 19.76 here, that's a bit precise, given that I've read off the graph to maybe plus or minus a quarter of a magnesium-calcium ratio. Okay, so think about when you're doing a calculation in a plug and chug kind of environment in an exam, what's the input precision? Therefore, what's the output precision? Okay. So we kind of went through this a little bit in the lecture, why you might change the oxygen isotope composition of the water. So light isotopes get evaporated out of the ocean, and then heavy isotopes progressively get precipitated out. So when you grow an ice sheet, it's got lots and lots of light isotopes in compared to the heavy isotopes. So if you grow a very big ice sheet, that depletes the ocean in light isotopes. Means the ocean gets more positive. So in glacials, you can see we have more positive. So one of the tricks that paleoceanographers kind of do when plotting graphs like this is they flip the y-axis upside down. So negative is up, which is a bit tedious. But they do this because both temperature and ice volume affect oxygen isotopes in the same way. So it kind of like warm and less ice, cold and more ice down here. So that's kind of why they do that. So again, so this last part of the practical was really looking at, quite often we don't have both, say, two proxies. We only have one proxy. We don't have magnesium, calcium and oxygen isotopes. We might only have oxygen isotope measurements. So that's in the calcium carbonate. So that's going to be a function of both the oxygen isotope composition of the water that they're precipitated from and the temperature at which they precipitated. So that leads to an error, obviously. So those tend to kind of correlate with each other in that when it's cold, you tend to have more ice on land, which means that it drives the oxygen isotopes in the same direction. But it's something you do need to kind of watch out for. So I guess this kind of question came up, a related question came up in the student staff consultative committees, that one of the things that you guys were a little bit concerned about is you didn't really understand why you were doing this course, in terms of why are we learning all this geochemistry. And the point, well, one of the points, is that you'll be seeing a lot of these kind of data, isotope data, trace element data, in the future, okay, in other courses, and maybe in the fourth year or fifth year if you go on to do that. And what we want you to do is be able to look at that data with a critical eye. And when someone presents you with an oxygen isotope curve and go, oh look, it was warmer, you go, is it? Was it? Really? Is that all temperature doing that? Or was there an ice volume effect? Okay, and we'll see in today's lecture there are also some other problems with using isotopes as paleotemperature proxies. So you need to be able to have the knowledge about how these systems work at a very fundamental level, right down to of how isotopes fractionate, to be able to critically analyse data in the future. So that's one of the reasons we get you to do this stuff. Anyway, so if we'd have ignored the temperature effect on oxygen isotopes and just assumed that it was telling us about oxygen isotopes of the water, we'd have got an answer that was very wrong, but still in the same direction, so still colder at the LGM. Okay, so again, I already mentioned this a little bit, talk about commenting on the accuracy and the precision. So you start out with something that you've eyeballed off a graph, and even if you hadn't eyeballed it off the graph and you'd done a nice average of these numbers, that would still have an uncertainty associated with it because of the natural variability, the imprecision of the measurement would have some uncertainty on it to start off with. So your input parameters into your kind of plug and chug, that has got some uncertainty to it. But also some of the equations that you've used. Okay, so for instance, this relationship between the magnesium-calcium ratio and temperature, okay, so that calibration line is this line on here. So you can see that you could probably fit other lines through those data on this calibration data series here. So there must be some uncertainty in these parameters, in these constants of regression here. Okay, so when we do a calibration of a proxy against temperature or whatever you're trying to reconstruct, there will be some uncertainty associated with that, which you should think about propagating through to your answer. So so just look at this as an example. So if we had a magnesium-calcium ratio of 2.5, but we were unsure about that, okay, it would be from 2 to 3, say. Now, if we just propagated our uncertainty based on the calibration line, we come across to here, and then down, and maybe across from here to the line, and down. Okay, so we'd be somewhere between maybe 13 and 16 degrees Celsius. But if we think about the uncertainty also on the actual calibration data set, we might go from here all the way across to maybe here and down, or from here just to here and down, giving us a much wider range of temperatures if we take into account the scatter of the data that's gone into the proxy calibration. Okay? So that's something to consider as well. And then also when you get a question like this, comment on the accuracy and precision. So what I've just described there is really commenting on the precision. Okay? So the accuracy would be, what are the other assumptions that go into that paleotemperature kind of equation? Okay? Are we at isotope equilibrium? Have the samples suffered diagenesis and re-equilibrated with another pore fluid, maybe pore fluid or another seawater? Okay, so those kind of things go into that kind of comment thingy. So if we get time at the end to do the practical, we might discuss some of those questions.